Okay, now we want to talk about some properties of definite integrals. The definition of a definite integral of f on the interval a to b specifies that a is less than b. Now, however, it's convenient to extend the definition to cover cases in which a equals b or a is greater than b. Geometrically, the following two definitions seem reasonable. For example, it makes sense to define the area of a region of zero width and finite height to be zero. In other words, if f is defined at x equals a, then we define the integral from a to a of f of x dx is equaling 0. Because you have no width. If you go from a to a, you didn't go anywhere, so there's no width to the region, so there can't be any area, so the answer is 0. If f is integrable on a to b, then the integral from b to a is equal to the opposite of the integral from a to b. Think of it like this. You're going backwards, so you should get the opposite answer. Cool, huh? All right, because the integrand is defined at x equals 2, the upper and lower limits of integration are equal. You can write the integral from 2 to 2 of the square root of x squared dx, x squared plus 1 dx is equal to 2, is equal to 0. All right, the integral from 0 to 3 of x plus 2 is the same as the one given in the example 3b, except that the upper and lower limits are reversed, so that the limits, since the limits are reversed, you give the opposite of the answer from the integral from 0 to 3. So since that was 21 halves, the answer from 3 to 0 would be negative 21 halves. So in this picture, the larger region can be divided at C into two subregions whose intersection is a line segment. In other words, the integral from a to b of f of x dx is this whole region. But if I split it up at C, it's actually the sum of the integral from a to c plus the integral from c to b. Because a line segment has 0 area, it follows that the area of the larger region is equal to the sum of the areas of the two smaller regions. So that's the additive property. If f is integrable on 3 closed intervals determined by a, b, and c, then the integral from a to b is equal to the integral from a to c plus the integral from c to b. Because the definite integral is defined as the limit of a sum, it inherits the properties of summation. In other words, you can factor out constants from integral symbols, and you can, if you have addition and subtraction inside the integral, you can split it up and add and subtract their respective integrals. So let's use the additive property. Evaluate the definite integral, -1 to 1 at absolute value of x. So if I draw a picture of this, absolute value of x, y is equal to -x when x is less than 0, and y is equal to x when x is greater than 0. So what I'd have to do if I want to get the area from -1 to 1, I mean, you could see it as triangles. Okay, I get that. But if I want to illustrate this property, I would have to split it up as the integral from -1 to 0 of -x, because that's the graph of this line, plus the integral from 0 to 1 of x, which is the graph of this line. So that's a half plus a half, which is equal to 1. Okay? And we could use the fact that these are triangles with a base 1 and a height 1. Excuse me, sorry. Evaluate the integral from 1 to 3 of this function using each of the following values. So they're telling you that the integral of x squared is 26/3, the integral of x is 4, and the integral of, this is technically, if there's nothing in there, it's understood to be 1, is 2. Okay, now be careful. The integral of x squared is not always 26/3. It's the integral of x squared from the interval 1 to 3. Okay, they have a interval defined there. So I can split this integral up into 3 separate integrals and then factor out the negative, the 4, and the -3. Then I can use the fact that the integral from 1 to 3 of x squared was 26/3, so this one is -26/3. From 1 to 3 of x was 4, so this is 4 times that, so you have 4 times 4. From 1 to 3, the integral of dx was just 2, so it was multiplied by -3, so it's -3 times 2. And if you multiply all those out, add and subtract them up, you get 4/3. So if f and g are continuous on the closed interval a to b, and f is less than or equal to g for a between a and b, the following properties are true. The area of the region bounded by the graph of f and the x-axis between a and b must be non-negative. So, oops. So this is saying that the y values are greater than or equal to 0, and g, the y values of g are greater than the values of f, greater than or equal to. So they also must be positive. So if both regions lie on or above the x-axis, or graphs do, so their regions must be non-negative. Second, the area must be less than or equal to the area of the region bounded by the graph of g. So since f is lower than g on the whole interval, its area or its definite integral must have a value less than or equal to the value of the definite integral of g. Down here, the definite integral of f is less than or equal to the definite integral of g, because the graph of f lies below the graph of g, and both graphs are above the x-axis. So those two properties are generalized in this theorem. If f is integrable and non-negative, must be non-negative, then the integral of f is greater than or equal to 0. Think about it. If the function has to lie above the x-axis, on or above the x-axis, the area under it is either going to be 0 or positive. So the definite integral is going to be greater than or equal to 0. Then if you have two functions that are both above the x-axis and g is always on or above f, then their respective areas or definite integrals, f is going to be less than or equal to the definite integral of g. All right, guys, that's it for this section. Please continue on to your assignments. And as always, reach out to me if you have any questions, and take care.